Okay, so for example, we have 3 different species up at the top. Human mushroom tulip. Get my pen here. Okay, so let me move this out of the way. Move that down here. Okay, so our human mushroom tulip. You see where I am here? And it shows the amount of differences between our DNA sequences. Okay, so human and mushroom DNA sequences are 30% different. Human and tulip DNA sequences are 40% different. And mushroom and tulip DNA species are 40% different, or DNA is 40% different. Okay, so there's 2 different ways we could show that in a phylogenetic tree. All right, I'm going to move this again now. Get that out of the way. Okay, so down here at the bottom, you see there's tree 1 and tree 2. All right, so we could say there was a common ancestor that split into tulips, and then we had another split here between humans and mushrooms. Okay, and that might seem more likely because humans and mushrooms share more DNA. Okay, that would make sense based on that 30%, right? The other possibility, though, is that mushrooms diverged early on, and then humans and tulips diverged later. Okay, so that is another possibility. Okay, the reason that we can say that it is less likely, which you can see down here at the bottom, it says less likely. Okay, the reason that one is less likely is because we add up the amount of genetic change, there's more genetic change on one side than the other. Okay, so if we add up the genetic change over here, we've got 10% and 25% equals 35% genetic change to get to a tulip. Okay, where we have 5% genetic change to get to a mushroom. On the more likely diagram, okay, this one says more likely, the genetic change is happening at an equal rate. Okay, we've got 20% over here on the tulip side, and 5 plus 15% over here on the mushroom and human side, which equals 20%. So this tree is more likely, tree number 1, because there's the same amount of genetic changes taking place. So that's how we decide how those phylogenetic trees are broken up. We have to keep the rate of change for the DNA as same as possible. Again, for organisms that are all living at the same time, which these are. Okay, I'll take a minute to erase this. As far as what you want to put in your notes, just a quick sketch of these 2 phylogenetic trees or cladograms would probably be helpful, and you can show the difference between which one has the uneven amount of DNA change and which one has the even amount of DNA change. Okay, I think this is our last slide, so we're about done here. The last thing that I want to point out to you is that phylogenetic trees, as I said, are based on DNA, which is molecular, DNA, RNA, or proteins, which is molecular evidence. But what scientists really try to do is they try to fit all the data. Okay, so not just, excuse me, not just the molecular data, okay, which is the DNA, RNA, or proteins, but also they try to make the phylograms fit the morphological data. That means what they look like. Okay, that's kind of where our taxonomy comes in. And fossil information. So we can get dates and ages of things from fossils and see those early ancestors, how old they were and how they seem to, the traits that they seem to have, so their primitive characters and things like that. So really what it comes down to is a combination of not only what we talked about in the last slide, which is the rate of genetic change, but also fitting these other categories as well. What does it look like? What doesn't it look like? What do the fossils say? So really we're taking all those things into account. So you want to write yourself a note of that. Get rid of some of this mess of scribbles I have up here. Okay, so again, we're just going to do an example to show what I mean by this. Okay, so the first one here, the first little phylogenetic tree, which is the mammal-bird clade, so this is a group that includes mammals and birds, say that, well, we could have had a divergence first, that the lizards went their own way, and then birds and mammals are more closely related to each other, right, because they share a more recent common ancestor, and they both have a four-chambered heart. Okay, so there's maybe a shared character right there that makes a shared derived character that makes the bird and the mammal closer related. Okay, so that would be the morphological data, right? They look the same. When you open them up, they both have a four-chambered heart, which would make you think that, okay, they're pretty closely related to each other compared to a lizard. However, when we look at the molecular and the fossil evidence, what we see is that lizards and birds are actually more closely related. They share a more recent common ancestor, and that mammals branched off a lot earlier. So actually what our clade should be is a lizard-bird clade. Okay, there's the clade right there. They are more closely related to each other than the mammal. So the evidence for the molecular and the fossil portion of this, okay, kind of outweigh the morphological or that four-chambered heart idea. So what about that four-chambered heart then? How do we explain that both birds and mammals have a four-chambered heart, but birds and lizards are more closely related? Well, they show in this diagram here that that four-chambered heart actually evolved separately 2 different times. Okay, so the four-chambered heart evolved down here for the mammal and right here for the birds. Okay, so even though they're not the closest related, they do have similar morphology just because that particular trait happened to evolve in both of them. And we see that in other organisms as well. Birds and insects, for example, both have wings. Does that mean birds and insects are more closely related than birds and other organisms that are warm-blooded, for example? Not necessarily, no. Okay, it just means that wings managed to evolve twice. 3 times if you throw in the fact that mammals like bats have wings. Okay, so really the point I want to drive home again here is this right here, that in order to make a good phylogenetic tree, it has to be a weighing of all the evidence. Okay, not just what do they look like, but also what does their DNA say and what does the fossil evidence show us.